All right. We're coming back from break. I'm just going to make sure they're ready up there. Okay. So we're going to have our first specialized lecture today. I mentioned the first day some of, we have the basic component lectures, and then we have some specialized lectures about topics that many people find very interesting, or some of the working groups and their activities. So today we have Isla Simpson. She's here in the climate analysis section. She studies global climate variability and change. And she's going to talk to us about idealized modeling or simpler models within the CESM framework. We mentioned there are lots of ways to run the model with the same code base, so you'll learn a little bit about that today.
All right, thanks. Is this on? No? Yes. Oh, it is? Does it sound loud?
Yep, you're good.
Okay. All right, thanks. So yeah, I'm going to talk about opportunities that you have for doing more idealized modeling within CESM. So this is the result of the work of many individuals, most of whom I've listed here, but no doubt there's other people that I've missed that have contributed to making these models available. So as you probably already learned, CSM consists of a number of different components, and they're all coupled together using the coupler. But even if you just take one of these components by itself, it's kind of complicated. So for example, if we take the atmosphere, if you want to run just atmosphere-only simulations, the atmosphere consists of your dynamical core, which is kind of solving the equations of motion on a grid on the sphere, and it's solving the thermodynamic equation. And then that's coupled to a whole suite of physical parameterizations where you have choices about how to represent them and parameters that you're choosing. And so these are trying to represent all of these different processes that are of a smaller scale than you can resolve on the grid that we're using. And I'm listing some of them here, but not all of them. And then even if you're running atmosphere only, you of course have to couple to the surface in some way. So you'll typically couple to the land model, and then you'll run with prescribed sea surface temperatures and sea ice. And so you can see that even if you're just focused on running atmosphere-only simulations, there's a whole load of complexity that's going on in here. And so what we typically do is we'll take CSM and we'll run it through a big supercomputer, and we'll come up with a representation of what the climate looks like. As an example, I'm just showing you here the historical period precipitation on the left, and then eddy sea level pressure, which you can kind of think of as a measure of the circulation on the right. This is in our CSM2 large ensemble, and so that's the present day climate, and then we'll typically perturb it in some way. For example, run a future scenario to see what is it going to look like at the end of the century, and we come up with some changes in precipitation on the left and sea level pressure on the right. And so that's kind of what you have to do if you're going to make climate projections. But the challenges come in when we try and understand why do these changes happen? Why is the model doing what it's doing? Do we trust it? And why does the real world behave the way that it does, as well as just the complex CSM? And so there are a number of challenges that we face when really trying to answer the question of why are things happening. One, as I mentioned, is CSM is complicated. Everything is changing all at once. The system is typically kind of in a quasi-equilibrium balanced state. It's always kind of solving the various balances that it's supposed to. It's conserving energy, conserving momentum, conserving moisture. And so what that means is that all of the components are very coupled. You change one thing and everything else responds to kind of maintain a new balance. And that can make it really hard to establish causal relationships and really say this thing is what triggered that thing. And then, of course, just to kind of speak to the complexity is you have to use a massive supercomputer to come up with the answer. And so it's not like we can just think about it and know what all the processes are involved are. Otherwise, we wouldn't need a huge supercomputer to come up with the solution. So how can we try and pull it apart and really understand what the model or the real world is doing? Well, there's a number of approaches. So one is you can just kind of do detailed diagnosis of the model output. You can go a long way with that, really digging into the various fields that the model produces and try and understand from there. You can use simplified versions of CESM, or you could perform idealized experiments with the more complex version of CESM. And so here, what I'm going to introduce to you is the various simplified versions of CSM that you might be able to use in your research to really pull things apart and try to understand them. So really, over the last kind of 8 years or so, our capacity to run idealized models within CSM has grown a lot. Mostly this growth has happened on the atmosphere side, but we're really moving now into the land and coupled idealized configurations as well. And so there's some new exciting things coming up in the coming year that I'll tell you about toward the end. So if you're not an atmospheric modeler, I'll be getting to the land and the ocean toward the end of the talk. So if you're interested, you can Google CSM simpler models, or this is the website here where you can find out about what we currently have available. So simpler models are really kind of stripped down versions of CSM, that they'll only contain certain components, or they'll contain idealized representations of certain components. And so I'll just go through some of the pros and cons of these idealized models. An advantage is that they can be easier to perturb. You have a bit more control, so you can change one thing and then see how do other things respond, and that allows you to run idealized experiments to kind of identify causal pathways. They're not all of them, but many of them are cheap to run, and so that means that some of these you can even run on your laptop. So if you have limited resources, you can run them easily, but it also means that you can run many experiments, and you can do parameter sweeps to really try and see how is the system sensitive to a given thing. On the con side, I'm just going to list one, but of course it's a very big one, and that these models are idealized, so they're less realistic, and so always bear that in mind. And I argue that you should always keep your eye on the real world, or full CSM, and be using these configurations to try and really understand something that you see in the more complex system. So I'll start by going through the atmospheric simpler models that we have available. And so this is kind of a depiction of the atmospheric model hierarchy. And this is where we're at in terms of availability. So all of the ones that are in the kind of turquoise color are available. They're not all available in CSM 2.0, but they're available in various releases of CSM. So these ones on the bottom left here, we don't have these. These are ones where you're really changing the equations of motion that you're solving, and that we haven't produced those. But the ones on the diagonal here, these are configurations where you have the full dynamics of the atmosphere, just like you do in CSM itself, but you have various simplifications in the physics or in the boundary conditions. And then the single column model over here by itself is kind of the opposite. You don't have dynamics, you're basically prescribing the dynamics, but you have the full physics. So I'll just run through each of these to give you an idea of what they involve, and there might be too much on the slides for you to pay attention to all of it now, but of course the slides will be made available. So the dry dynamical core, what this consists of is basically you take all of the physics parameterizations in the atmosphere model and you strip them out, and you replace them with a very simple relaxation of the temperature field towards some specified equilibrium temperature profile. So this is a very idealized representation of the physics. There's no moisture, there's no clouds. You have a very simple linear drag on the winds at the lowest model levels. And this can really be good for problems where you really want to explore dry dynamics. You don't care about the interactions with moisture, but you want a cheap configuration where you can look at things like jet streams or eddy mean flow interactions and things like that. So an advantage of this is very cheap to run, and it's also very easy to perturb. So you can do things like change that relaxation temperature profile, look at what happens if I make the poles warm? How does that affect the mid-latitude jet streams? There's those kind of questions that you can start to look at with this simplified configuration. So if we move on up the hierarchy and we go to the dynamical core with idealized moisture, this is pretty similar to the dry dynamical core that I just described. But the addition here is that now there's a very simple representation of moisture. So you have a water-covered Earth. You have a simple representation of evaporation. The moisture is evaporated, it moves around, and when it becomes saturated, it precipitates, and you get heating associated with that. Much like you do in the real atmosphere, but it's a pretty simplified representation of the moisture. So this, again, is very cheap to run, but the advantage over the dry dynamical core now is that you can look at the transports of moisture, and you can look at the interaction of weather systems with moisture and the heating in a simplified way, and you can look at things like precipitation in this configuration. So if we go now on up the hierarchy to go to the gray radiation aquaplanet, this is actually the most recent release. This was released into CAM last week, And so I don't have when it's going to be in CESM, but you can download CESM, and as if you use that CAM tag, this should be available to you. So the gray radiation aquaplanet, if we start with that one I just went through, the dynamical core with idealized moisture, the way we move up in complexity now is instead of this simple relaxation of the temperature field, we now have a very simplified radiation scheme. So it's simplified in that there's no clouds, there's water vapor in the model, but the radiation doesn't see it. You just have an incoming shortwave band and one long wave band, and you specify the concentration of the long wave absorber. So now in this configuration, you can start to look in a simplified way at the interactions between radiation and the circulation. So this one's set up following the study by Frierson et al. And you can start to do kind of idealized global warming experiments because you can change the concentration of that long wave absorber and look at how things respond, but it's still a very cheap model for running. Okay, now we go out to a radiative convective equilibrium world, and now we're in the realms of models that aren't actually that cheap to run. They're almost using all the same complexity of CAM, but they're simplified in their boundary conditions. So radiative convective equilibrium is basically a planet that has no rotation, and it has no latitudinally varying solar insolation. You just have a very uniform planet and this balance between radiation and convection. And so this can be a nice kind of idealized setting. It's been used a lot in this radiative convective equilibrium model intercomparison project to look at things like how does convective aggregation change with warming? And you can see in this example here, you've got all this convection at the lower temperature, and when you go to the higher temperature here, it aggregates a lot more. So this is useful for looking at things like convection, but in a very idealized setting. Then we go up to the aquaplanet, which is even less simplified. The only simplification here in the aquaplanet is that you have a water-covered Earth. You just don't have the land model. And so this is useful for many reasons, in that it just has much less complexity in terms of the asymmetries in the circulation. If you want to look at things like tropical cyclones, you can get really good statistics because it's all uniform in longitude. You can look at things like tropical waves in this example here from the description paper from Brian Medeiros that you can check out if you want to learn more. So the final atmospheric configuration that I just want to mention here is the single column model. And like I said before, this is kind of the opposite from the ones on the diagonal. These all have the dynamics, but simplifications in the physics are the boundary conditions. And the single column model, you prescribe the dynamics. So basically what's done here is you're just taking a single location on the planet and you're prescribing what the circulation is doing in terms of bringing in moisture or heat, but you're solving for the full column physics in the atmosphere model just at that single location. So this can be useful if you want to look at things in a very constrained setting where you want, all of your simulations can experience the same weather, but you can perturb parameters in, for example, your convection scheme or whatever other microphysics parameterization you want to, and look at how that affects things like clouds in this very simplified setting. And this is one you can run on your laptop, and there's actually a containerized version that you can download to run it on your laptop. Okay, so now I want to move on to simpler models on the land side, and this is the newer developments that are coming soon. So we have this simple land interface model, which was developed by Marisa Legou when she was doing her PhD at the University of Washington. So CLM5, if you haven't learned about it already, you will. It's very complex. There are many different processes that go into CLM. And many of the features of CLM are kind of emergent from these processes. So things like the leaf biomass or the albedo or the roughness, they're not things you specify in CLM necessarily. They kind of emerge as a result of CLM's interaction with the climate. And if that can make it hard to do kind of idealized experiments where you say you want to change the albedo over a region and see how does the planet respond. That can be difficult to do in CLM. So this simple model kind of allows you to look at land and its impacts on the broader Earth system in a more simplified setting. So it's basically going back to kind of the olden days of land surface modeling. It has a simple representation of the soil and transfer of heat through the soil column. You specify the vegetation height, which determines your roughness. You also can specify the albedo. Snow falls on the land model, but you can specify what depth the snow needs to be to kind of cover your vegetation. And then a big simplification is this bucket hydrology, where you basically just have a bucket that you specify how deep that is, and that controls how much water you have available to evaporate, along with some other parameters that you can specify. So it's much simpler, and it can allow you to really perturb things and say, how does water availability at the land surface change my extremes in this simplified setting? You could ask that question and try to answer it by, for example, changing the depth of the bucket to change the availability of water in this simplified model. So this is coming soon. It is available. If you're very interested to get started running this now, you can email me and I can tell you who to contact to do that. But this should be coming by the end of the summer, maybe into the autumn, before it's kind of fully released in a supported way within CSM, but it's coming soon. And then the final thing I just want to mention, there's some ongoing efforts for coupled idealized modeling. So we've had this project for the last couple of years that has been funded by NSF to really simplify the setup of your own idealized coupled configuration. So just the kind of things that this is targeted towards. An example here is you could have a coupled aquaplanet where you say you want to put a ridge and see how does just doing that give you an ENSO, for example. Those are the kinds of questions you might want to ask in an idealized setting, or in this case, what is the impact of the North American continent, like having some idealized continent? How does that change if you run with a coupled ocean? How does that change if you have complex land surface properties? Those kind of things. You want to set up your own ocean bathymetries, your own continental geometries, your own land surface properties. This tool is really geared towards allowing you to do that. So the starting point is going to be this GUI, which you may find useful just in general. It doesn't have to be for simplified models, where you can kind of pick the different components you want to use, and then it'll tell you, are they compatible? And it will also guide you through the setup of idealized configurations. It'll guide you to a bathymetry tool and how to use that, where you can say, this is how I want my ocean geometries to look like. It'll guide you to a land surface properties tool, where you can specify what kind of land surface types you want and where. And it'll help you through the process of coupling those components together to get your more idealized configurations. So these are kind of examples just of what we kind of envision people doing with these tools. Suppose you wanted to know, well, what would happen if I filled in the Indian Ocean? How does that change the climate? Or what is the impacts of deforestation? Suppose you wanted to say, okay, we've lost forest in this region, it's become farmland or grassland. How has that changed the climate? And so this will allow you to perturb the components in this kind of way to try and answer those questions. So again, this is coming soon, probably a little longer timescale than the last one, but I think within the next year, these tools should be ready and available. And if you're interested in testing them, please send me an email. We can make them available to you sooner, and we're definitely looking for people to test these and see where they might be going wrong before we release them to everyone. So to conclude, simpler models are a valuable tool to kind of gain process level understanding of the broader CESM and the climate system in general. Many of them are cheaper to run, although not all of them. Some of them, like the single column model, you can even run on your own laptop. They're also well documented, and we have a lot of instructions for how to modify them. So kind of things like changing the source code. If that's something you want to get into, you'll learn a lot this week. But we also have instructions that where you might, if you want to start playing around with that, the simplified models might be a nice place to start to just kind of get a handle on making source code modifications. So you can go and see the Simple Models website to read more. There's a mailing list if you want to hear about updates. And you can also post queries about the configurations on the bulletin board. And my email address is there, and I'll be happy to answer questions for the time we have left.
All right. Thank you, Isla. All right, you guys know the drill by now. Questions?
Does the SCAM model have chemistry?
I think it doesn't at the moment, but there was an effort to do that. I would have to ask the person involved as to where that is at. Definitely out of the box at the moment. I'm not aware that it does.
Other questions? People over here? No, can you just pass it right behind you? Cool.
Thanks for a great talk. Maybe this is a vague question, but there's an underlying assumption in the simple models framework that you can infer causality, maybe by linearizing the system. Is it true, or I mean, do you have any sense of when you include the nonlinearities back in the full coupled sense that these causal frameworks will be robust? Or are they like, they have limited applicability? And even if one were to start thinking about bridging the simple to the coupled, like what would be a good way to do so? And I guess it depends on the system.
Yeah, so by nonlinearities, there's many different types of nonlinearities. There could be, all of these are nonlinear in terms of the equations of motion that are being solved, but things like interaction with the ocean, for example, you wouldn't have if you were looking at a dry dynamical core. And that's, yeah, I think it's a very good point. You should use the full hierarchy and use the configuration that is most applicable for your problem. I think, I think if your starting point is something that you've seen in the real world or in CESM and you want to explain it and you have an idea and you go and put it in the simple model and it produces the same thing, I think the null hypothesis should be that your argument is correct. Of course, anyone can be skeptical and say, well, if you did this, then that wouldn't be true. But you have to start somewhere. So I'd say span the hierarchy and use the tool that seems most relevant to your problem.
Sorry, can I follow up? Yeah, maybe I was exactly as you said, the ocean interaction part. So I was just trying to think of even like a good example to like argue with this question. And so maybe I should find you offline and think of like I come from a statistical background, so I wonder about these things like even in
I can give you an example.
Yeah.
People have done experiments where and this is not in simplified models necessarily, but you could have a slab ocean, for example, which is basically just a thermodynamic ocean. It doesn't have the ocean circulation. People did Arctic amplification experiments where they kind of removed sea ice and they got a particular response. They got a lot of warming in, say, I can't remember which way around it is, but they got a particular response with impacts, to a certain region. And then people did it with a coupled ocean, and they got a very different response because the ocean circulation responded. So yeah, there are many examples where if you just go and blindly perturb something and get your response, you could conclude that there's a connection there that wouldn't be there in the real world. So that's where I think you need to kind of use it all and verify that there's evidence for what you find in the idealized models by then going back to CSM and being, okay, do I see the same mechanisms happening there? Or is there something more when you start to look at it in the more complex system?
Cool. Hey, thanks for the talk. Yeah, so for the GUI, I assume, is that going to be mostly for more standard like setup cases if you're going to run something a bit more like complicated or using something like something scientifically unsupported, like a comp set, I guess, would you not be able to do that with the GUI?
Well, the purpose of the GUI is hopefully it would encompass all of it. So if you wanted to run a scientifically supported comp set, you could either do it through the GUI or you could just use the comp set. This is more designed for doing unsupported things where you want to mix and match different components to tell you kind of how to do that. And especially for these coupled idealized configurations, I mean, none of them are going to be supported because they're going to be new ideas, new geometries that people want to use. So it's kind of to help you guide you through that setup. And of course, that comes with your own risks. You need to be aware of like making sure that it's like okay, it doesn't have some huge imbalance at the top of atmosphere, or is drifting massively, or making sure that it's spun up and things like that. But this would be a start for you to get your own unsupported configurations.
All right, more questions? While you think about it, I was just going to say, along what Isla just said, we've talked about the comp sets that exist, and there's a link in the activities that you go through that talks about all the comp sets, and in there it says if they're scientifically supported or not, and I think you should always be aware of that and know what you're using and be able to check it and make sure what you see is sensible for what you think that is there. Just using the model directly out of the box and assuming it's always right is probably going to lead to problems, because we know that all models are simplifications of the real world. They're not right in every way, but just wanted to point that out. All right, so any last questions? All right, well, thank you, Isla, very much.
Thanks.
And I think Isla is doing Meet a Scientist. Is it tomorrow? Thursday. Okay, so some of you will have a chance to talk more with her that day. All right, so. Okay, so there's one thing I keep forgetting to tell you all, which I tried to remember this morning. There are power cords underneath your seats. There's like a black bar, and there are both USB and regular power outlets in there. Someone asked me about this, and I was like, oh, well, I don't know. So anyway, I just remembered that, and I wanted to let you know. All right, so the kind of last activity before our daily debrief is our lab exercises again today. And let's see if I can highlight these nicely. We're still going to do a debrief in here from 4:30 to 4:45, but just before we break up, I just want to do a check-in. So did people who were using the reservation queues, did everything work a lot more smoothly this morning? Yes. Yes, so that's a good question. Okay. All right, so these queues were only set up, and probably the reason it might still be sitting there is that this reservation ended at noon today. And so as soon as noon hit, it was like, nope, can't use this queue anymore. We're not sure. Yeah. Mm-hmm. Okay. Okay, so if you're having issues submitting to the particular account, I do have the project account up here, and I did provide. This is slightly changed since this morning. Sorry, we're making changes as we get feedback from you guys, but you can change the project number you're submitting to. I think this was more of a profile issue if they didn't somehow have you on this account correctly, or your when you logged in it wasn't referencing it correctly. But if anyone else has that issue, let me know. Yeah. You should not have to. If you've done the profile thing, it should, every time you log in, it'll look and it'll set your project to this project for the duration of the tutorial. If you want to be extra sure right before you submit a job, you could just run this every time, but it shouldn't be necessary. You can also check in your env run file to make sure that that project code is set as it is here. But I would always check this job queue one, and it might actually be env batch, not env run. Yeah, so the profile file is just calling a file that we set for this year's tutorial that loads the modules we think you'll need and set some of these default paths. So it should have set your project automatically to this project so that you're charging for that this week. And then after this week, you could delete that and charge to whatever your default account is if you have a normal project account. But yeah. All right, I saw a question. Wait, there was a question there. Yeah. Okay. Okay. That's good to know. I'll add it to my like things to deal with next year. The main thing is like when you're building the model, it doesn't actually cost a lot. So if you do have another account, it shouldn't be a big demand. It is running the model that we've had people who've come before and they had a different account and they ran and then they accidentally like totally depleted their account and we're like, well, sorry. We'll try to fix it. So that's a good thing to note though. All right, you had a comment. Mhm. Yeah, so some of the rooms did a Q move command. It's not because this changes your XML file. The Q move, which is one of the PBS commands that you can use, just is on the PBS side. So it would not change your XML file. It just says, okay, move this job into this other queue. You could run into issues with that with PBS. So like, I think the thing is with this reservation, they've said anyone who has the usernames of all of us can use it, but like the regular scientists up here, they can't run to that. And so you could run into issues with that. It's not a bad thing to do. I asked, after I learned about that yesterday, I queried the scientists and most of them were like, I didn't even know you could do that. So most of us have not done it. All right, are there any other questions or things that went not super smoothly today? Okay. All right, well, without further ado, we're gonna have more of the helpers showing up pretty soon, but we'll, I'm just checking if they're outside. Some of them are. Hang on. Helpers want to come in for a minute? Okay. There will be more than just these folks. But one thing I noticed was I asked everybody if they had finished the basics exercises and no hands went up, and then there were many questions about the basic exercises. So that's okay. I'm not going to ask you to identify where you are by raising your hand. I want to emphasize that we really don't care where you are. Our goal is to help you at whatever stage you are. And there are people here who are like, I've been using Unix for 10 plus years. And there are people who are like, I've never used Unix before. I don't know what CD means, all of that. And we don't care. We just want to help you where you are. So along those lines, the reason we're splitting you up by these groups is that we want to make sure we have the right number of helpers in each room for the number of people there are, maybe where you are along, so that by the end of tomorrow, hopefully we've all gotten through these kind of communal exercises so that you can go into the diagnostics and the challenge exercises having completed these, because otherwise you really won't be able to do the challenge exercises probably. So that being said, if you're working on the basics exercises or the XML exercise number 1, if you could go to the daemon room, either inner or outer, whatever's fine. The inner room is like on this side. The outer room is that area with the couches, since I realize that might not be clear to everyone. So if you're working on any of the basics exercises or the XML exercise number 1, go to the Damon room. If you're on XML exercises 2 or 3, please go to the library. And if you've finished the XML exercises and are on to name list or another exercise, go to the Chapman room, which is just past the library. If you need help getting there, let me know. All right. We have Sophia is helping again. If you want to wave, maybe we should have like bright yellow name tags so you know who the NCAR employees are. But Hui is helping again. I think Zhang is helping. He's out there, and there'll be more people showing up.